It's time for more melodious droning about a random bit of spectroscopy that's going to be important in organic chemistry. And this is IR spectroscopy. This has to do with molecules absorbing energy in the infrared part of the electromagnetic spectrum. One thing that'll be kind of important to keep track of as we go through these different types of spectroscopy is to see what exactly is happening on an atomic level given a particular energy on the spectrum, right? And so back in NMR days, we were kind of over here with these long radio waves. And one of the things you can tell is that this is not a very high energy kind of region. So we've actually gone quite a bit of an exponential gain in energy here. And you'll notice that this is the infrared range. And of course, there's the visible range that are the very narrow bands that our eyeballs can see. And so what we're going to kind of just run through real quick is a little bit of a review of NMR and what we were looking at there. And then what is so much more special about the way that this particular kind of energy interacts with molecules. Back in our NMR days of lore, so long ago, we talked about the fact that nuclei of particular atoms, well, actually every atom, spins in a certain fashion. And so here's just kind of an example of what you might imagine is the very center of an atom kind of spinning around. And of course, when you put it in a magnetic field, we saw this kind of split between spin states, and we looked at proton NMR and also C13 NMR, and it just so happened that they have one of two spin states. And so what you can see here is that we've got this nucleus that's kind of spinning of one of two directions, and of course we didn't talk too much about the way that these things precess about their orbit. It's really not that important. The important thing was to recognize is that in those systems that we previously looked at, there were two different spin states when you apply a magnetic field. And then what we do in the NMR spectrometer is that we hit it with some really low energy electromagnetic radiation, right? This is the radio wave coming in. And what happens is that it absorbs that particular bit of energy if it happens to be perfect. And what we measure in the NMR is kind of the relaxation of that thing. So what we're going to see here is that an IR is very different. By the way, these slides I'm going to make available underneath this module. So make sure you take a look at this. It actually has a bunch of really detailed notes that I'm probably going to completely ignore. Just because we as organic chemists, we're really looking to determine structures of organic things that we might be interested in. So the first thing we should talk about is what exactly is this IR measuring? And probably the easiest way to understand this is with a pretty simple system. So what you're looking at here are two different HF molecules. Of course, as we as organic chemists are not too interested in this particular molecule, but it'll kind of demonstrate what IR is doing to a molecular compound. One of the things you'll notice is that there is almost like in this HF bond, it's almost like there's kind of a spring between it that's kind of going boingy, wingy, wingy, wingy. We call this molecular vibrations, and it turns out that the frequency of this is at a really particular resonance. And so one of the things that I like about this little animation, which is available via hyperlink on that last slide there, is that it can kind of show you what happens when you make one thing that your spring is attached to much heavier, right? And so you can notice that when I make that proton into a deuterium, that the spring constant actually goes down quite a bit. And so all these, you don't have to worry too much about the quantities of these different things, but you can see here that that crazy looking thing, which is called the wave number, kind of cuts, it gets much lower, right, when there's some sort of heavier atom attached. Right? And so really when you look at even the most complicated IR, really what you're looking at is some sort of molecular vibration, right? Either this kind, which is called a compression vibration, or other types of vibrations, which we'll see in just a second, called WAGs. And of course, you could really get in the weeds with this and talk about symmetric vibrations and non-symmetric vibrations and asymmetric vibrations, and they all have their kind of place in different types of spectroscopy. So in IR, what's happening is that because of the molecule's vibration, it'll interact with electromagnetic radiation in the IR spectrum in a really particular way that we're going to take advantage of, and hopefully it'll be a little clearer in these next couple of slides. So here's water, which is a compound that's of a little bit more interest to us as organic chemists. And one of the things that you'll notice is that as a molecule gets a little bit more complex, the number of vibrations available to it goes up. So like for instance, this is called a symmetric compression. This is called an asymmetric compression. And then this guy is called a WAG, believe it or not. And so all of these energies, which you can kind of see here represented as wave numbers, which is a really weird unit, which we'll talk about a little bit in just a second. You can notice that the energies of these vibrations appear at different points on the spectrum, right? At different wave numbers or different energies is another way to think about it, right? Another thing which you'll notice is that a WAG, right, at like 1650 inverse centimeters is about half of the energy required to do any kind of compressionary type of vibrations. And we don't care too much about that in the spectrum, other than the fact that it is kind of good to keep in mind that these numbers actually mean something. It actually means something in terms of the energy of that particular vibration. But let's take a look at a slightly more complex system, and then we'll just kind of stop looking at these crazy animations here. And so, of course, this is the simplest organic, methane. And you can notice that there are a whole bunch of different modes of motion for these vibrational frequencies. Here's just a couple of them. They're just kind of fun to watch. And then, of course, like as you get more and more complex, there are more and more possibilities for these different molecular vibrations. And so what happens is you get really complicated looking IR spectra, which I'll show hopefully in this very next slide. Here's just a random organic thing. I just kind of stole it off the internet. And one of the things that you'll notice is that first of all the peaks kind of look inverted relative to what we were talking about NMR. There's this really particular frequency range here, which we're going to see here again and again, right? It runs from about 500 wave numbers to 4,000 wave numbers. One thing that's probably good to keep in mind is that the energy of these various molecular vibrations increases as we move to the left. So as you follow this arrow, hopefully you can see that arrow, energy is increasing in that direction. You'll notice this y-axis called percent transmittance, right? And so that really does mean, how much light is actually being let through a sample cell. But you look at this incredibly complicated set of peaks. The absolute last thing that you should do to these IR spectra is to assign every single one of these peaks, because it will hurt your brains. That is not what I want you to do. That's something that, was taught to me or attempted to be taught to me. And it is just incredibly unuseful unless you are studying exactly what physical principles are going on behind, the IR spectrometer, which we don't care about. We just care about the structural information that it gives to us. So I'm going to show you in the next couple of slides the kind of overarching thing that you should get out of this presentation. And then we'll go through and do a slightly more complicated look at every single major organic functional group and kind of different things that as you get better at this, you're going to start to pick up. But I really think it's important that you recognize that really when we look at an IR spectrum, what I want you to do is to look at about 1500 and go up to right about 4,000. I don't want you to worry about anything down here. This is actually called the fingerprint region for a reason, because there's going to be a whole bunch of different peaks. And really the only good thing that a lot of these peaks are good for is to recognize what you have by kind of identifying the fingerprint region of one thing and matching it to another. We're not going to do that. What we're going to do is we're going to concentrate on really particular parts of the spectrum. For instance, right here, that peak, even though it looks just like the other peaks, is hugely important in terms of us being able to assign the structure of vanillin here. This peak is hugely important in assigning the structure of vanillin. And one of the really cool things, at least I think it's cool, is that in NMR, we got all kinds of information about like the carbons and also the hydrogen environments. But one of the things that we didn't get much of is, these other functional groups, right? We saw a little bit of a way that you can figure out that something is an alcohol and a proton NMR, but it's not great. Same thing here, right? This aldehyde group, we might be able to tell a little bit of something about that carbon in C13 NMR, but, is there a way that we can really confirm that something is an aldehyde relative to like a ketone or anything else? And so that's what these slides are all going to be about. I like to think about IR as something that it doesn't really stand alone for us, right? We look at the we look at the NMRs, right? The proton and the C13, and then we build in the IR to kind of help us out for the things that the NMR is not very good at showing us. So what you should do is you should print this out and you should have this next to you, because these are the really important things that I want you to recognize right off the bat, right? And we'll just kind of go through a couple of things, right? This C double bond O stretch turns out to be incredibly diagnostic. So if I were teaching this in class, I'd say look at 1700 thereabouts, right? And look for a really nice intense peak, which you'll see some examples of in just a second. Another thing which is really important to look at is this region from let's say 2000 to, 2600 or so, usually is flat as a pancake. It turns out if there's a triple bond in there of either of these two types, usually there'll be some little tiny peak there, right? And so really what we're going to be doing every time we look at an IR is we're going to be looking in particular regions and saying, is there anything interesting there, right? Is there a peak at 1700? Is there nothing like there should be nothing between 2000 and 2600 or so? A lot of people spend a lot of time in this particular region right here, which is called the CH stretching region. What I will say is that this little region right here, we're going to treat almost more like a fingerprint region, just because we're in organic chemistry class, right? So a ton of things have CHs. The only really interesting things to come out of this region, as we'll see in a second, are different aldehyde peaks, which aren't even listed on this slide here. And then if there's some sort of alkene or alkyne, you might have an intense peak somewhere over here that you wouldn't otherwise see. Like I said, we'll see this in just a second. Probably the most important thing, in addition to this carbonyl and this relatively boring region right here, is this OH stretch region, right? Technically it overlaps with the NH stretch region, but if you see some sort of big moundy bit of crap out here around between 31 and 3600 or so, that's indicative of some sort of OH group, and sometimes it might be indicative of an NH group. But we're going to be able to kind of look at a couple of different examples of things that contain these groups and make some really important structural determinations. Okay, so if you watched that first 12 minutes or whatever it was, you've pretty much gotten everything you need to do the IR lab that's due next week. What we're going to do now is we're going to take a look at individual functional groups, and I'm going to kind of expand on some of these themes, right? We'll see the kind of the major areas that I just talked about, but I'll also show you a couple of extra things that are really things that you'll start to recognize as you look at more and more IR peaks over the next 3 terms. So for instance, right, I put the structure down here. Usually you wouldn't know the structure, but in terms of learning this, it's probably important to start somewhere. So I just kind of arbitrarily started with aldehydes, right, which is this little functionality right here. And so a couple of things that is important from that last slide. Remember, we're going to look around 1700, which is one of the first places we look to make sure that there's a big giant peak there. If there's a big giant peak somewhere in there, we know that there's a carbonyl. And so that's really the only super interesting thing that you see here, even though that you might see that there's all kinds of different arrows pointing at different things. If we were had already been through, let's say, an organic chemistry class, and we were coming back for advanced organic, we'd spend more time talking about these peaks, but I really don't care about them. One thing that kind of will differentiate an aldehyde from a ketone or something like that, keep in mind a ketone would also have a peak that looks like this. An aldehyde typically has this little peak right here, which is labeled B, which is actually due to this bond right here, a stretch between that carbonyl C and that H. When we get on to, for instance, take our ACS exam, this will become a little bit more important, right? Like we'll be able to narrow it down to a ketone and an aldehyde, and that might actually allow us to answer the question correctly after we've narrowed it down. But for today, doesn't really matter. By the way, in your lab, I included a correlation chart that includes all kinds of detail. And another thing which is really helpful for you guys to do is to develop your own correlation chart. In other words, like your own kind of little IR spectra that you kind of highlight certain areas of. Let's go on to the next one here. We don't really care about all this other stuff, but here's just kind of the important stretches that we really care about here. And so, by the way, like this is obviously in the fingerprint region right here. That CH bend, well, no duh, everything's gonna have a CH bend, right? And so that, yes, like when I learned this, I went through and assigned a bunch of these peaks, and then like we learned that when there's an intense peak, there's oftentimes overtone bands that are like some multiple of that thing. So there's an overtone band for a CO stretch. All that stuff is just so unimportant to us that you can just ignore it. Here's a real typical ketone, right? And so once again, we're going to concentrate on that peak around 1700, right? And everything else, who cares? Yay, we got some, CH stretches. Well, no duh, we're in an organic class. Of course, we have CH stretches. And you can also start to see that, this fingerprint region looks very different, right? Relative to something else, but we're not going to spend too much time talking about what all these other silly little peaks are due to. A spectacular use for IR is to identify a carboxylic acid. And I always can tell a carboxylic acid if you give me an IR just very quickly, because what is true is that there is this huge mound of junk, right? I don't care what's underneath that mound of junk. I don't care why it's a mound of junk. I just know that a mound of junk in this region is usually tells us that there's some sort of carboxylic acid there, right? And so there's that carboxylic acid. And just like all these other carbonyl containing groups, there should be a peak around 1700. And of course, like if we really cared, we would say, well, why is this at 1710 and not at 1690 and all that other stuff? That'll come. Don't worry about it. The important thing is to recognize a general form of a carboxylic acid. So again, don't worry too much about this, but it kind of labels, why is there a big giant mound of crap? Well, it turns out having to do with the OH stretching vibrations, and even more than that, hydrogen bonding and stuff like that. It's also important to recognize when you don't get a very exciting IR spectrum, well, an ether gives you a very unsatisfying look, right? You'll notice that there is no longer a peak at 1700 because we no longer have a carbonyl. We've got some peaks at, the CH bend area, but they're boring. There's nothing too exciting going on there. There's no big giant mound of crap out here. There's no kind of peaks in this normally very quiet area. If we were, really cared about assigning this thing as an ether, which I think there might be one question in your handouts, it turns out that this peak right here in the fingerprint region, like a super intense peak around like 11 or 1200, that's usually due to some sort of CO bond stretch. Do we really care? No, because it's in the fingerprint region and your brain will hurt if you go there. Other fun functional groups to drone at you about. Well, an ester. There's my carbonyl. And look, there's my carbonyl, right? It's about 1730 or something like that. Another way that you can tell there's an ester once we get a little bit better at looking these things is we look for some sort of intense peak once again around 11 or 1200, because just like in the last example, we had that nice stretch right there. I guess probably it's more likely this one between the sp3c and the O, right? Again, you're going to see that semi, important peak there. Do I care that you can tell the difference between an ester and an ether? Well, yeah, you should be able to tell that there's a carbonyl present in one, but it's, not super important other than that. An important thing, however, is to be able to tell that something is an ester and, let's say, maybe not a carboxylic acid, right? If we're deciding between two isomers, right? You'll notice there's a very quiet region out here. There's no big mound of crap that's indicative of a carboxylic acid. So that's just kind of one of the ways that used with NMR spectroscopy, this can be really helpful. Here's a general look of a pretty simple alcohol. The reason I show you this is that we've got this really kind of less moundy than the carboxylic acid peak, but still a very intense mound out around like 3,400 or so. That's indicative of an OH group. So I kind of think about in IR land is that a carboxylic acid kind of makes this thing a little messier looking, right? And then an alcohol is a little bit more intense and a little bit nicer to look at. And of course, that guy is due to the OH stretch vibration. Sorry, I didn't mean to click on that guy. And so one other group that we'll take a look at here is an amine group, and notice how different it is from an alcohol. So here's a typical amine, and the area that we're going to look at to identify an amine relative to, let's say, an alcohol or something else is what I think of as kind of double cow udders. Usually with primary amines like NH2 amines, these kind of like double udders appear, and they're kind of immediate of an intermediate intensity or percent transmittance. And of course, there's other interesting stuff out there that if we really cared about it, we might talk about the fact that right around 1600, there's this like NH bend. Nothing terribly interesting other than that, though. There's probably a little too much going on in this slide since it's got both an alkene and an alkyne going on. But different areas that we've kind of learned to concentrate on. First of all, notice that this region from like 2000 has, well, actually a couple of peaks, but typically there's just one. So like, let's look at this guy, right? And that's so probably due to this CC stretch right there, right? And so the fact that we don't have a quiet area out there usually means that there's some sort of triple bonded sucker. Another couple of important things are this guy right here, that really intense peak, right? Really sharp and really intense peak. That's actually due to a CH stretch for what's called a terminal alkyne. And so that's something that'll be diagnostic eventually. Other important things are the CC double bond, which is strangely not labeled, happens usually around 1600 right here. It's pretty close to like a CO double bond kind of thing. Also, this little sp2ch stretch is kind of a new one. Usually we don't have any kind of sp2 carbon stretches. And so this guy is new, right around 3100. Again, that's not something you need to know right now, but something we'll definitely build into the picture. Very last thing we're going to look at here is this aromatic. And we could spend a lot of time talking about all the craziness here, but one thing I'd like you to notice is that this region from like 1600 to 2000, it quite often has this kind of wave pattern right here. And that is almost always due to some sort of aromatic. So I just called this the wavies, right? So here are the wavies. And that's really common to some sort of benzene ring containing thing. This is a little bit complicated for students sometimes because it turns out, depending on the symmetry of the situation, like these guys can sometimes go away. Not the best diagnostic, but it's definitely something to keep your eye out for. So what you should do at this point is you should go look at all those different handouts that I just uploaded and made available. And what you'll see there is a very similar kind of, 5 or 6 handouts that you guys should be able to work your way through. I'd start at handout 1 and work my way on to handout, the last couple of handouts. And one of the things that's going to be important as we build this spectroscopy picture is that you continually improve your proton and also your C13 NMR ability. So that'll kind of be something that we do in those later handouts. That's enough droning. If you have any questions, talk to me in office hours. Bye-bye.